Okay, so we're going to look at Lisp, and I've already given you a tour of Lisp, and you've started on your implementation, so you understand Lisp to some degree there. And if we were to just look at programming in Lisp, that introduction I gave was probably enough for you to go to the Common Lisp manual and go and understand how Lisp works. Okay. So what's going to be different in what I'm going to talk about is that I'm going to actually talk about implementation. Okay. And we now have to do something different for each kind of atom. Okay, for an integer atom, we have to call an integer expression factory. For a double atom, we have to create a double expression factory, and we have to go in do integer factory.new instance a.getValue. Okay, assuming a is not an identifier, I should have sort of mentioned that. Okay, so is it? Okay, so need a different eval for each kind of. Okay, now let's go and talk about the complex composite function call eval. Okay, so we are not calling eval on any arbitrary S expression. We are calling eval on function applications. Okay, so that's going to be a tricky one, and we're going to look at just first the eval, assuming the basic Lisp stuff that you got in assignment 1, the basic, and so I'm talking about basic functions in Lisp interpreter and function definition in Lisp interpreter. So the functions you can call in Lisp interpreter are those that are directly implemented by the native language or that are implemented by the programmer using Lisp. Okay, so let's assume that the functions we are calling are the ones implemented directly by the native language. That's what your first assignment is about. Okay, so let's go and see how that is done. So we have two kinds of operations, basic operations. One are the familiar operations that are in other languages too, arithmetic, logical, relational, I/O, and so forth. Okay, their meaning is not a mystery. We just have to figure out how to invoke them from Lisp. And then there are some basic operations we implement in the native language. Okay, those are the predefined operations in Lisp, about which we need to explain a little bit more. Okay. And these are the list I think we have in your assignment 1, some implemented by Andrew in the interpreter and some implemented by you. And again, for those of you who are understanding, just to get an idea of how you guys are understanding, let me ask these questions. So firstly, I use the word extendable here. What would the word extendable mean in this context? You can add more. Of both kinds? And so, there's some basic, for instance, the initial one, we didn't add any I/O, but I'm asking, but actually in the version 2, Andrew has some I/O operations. So we might want to add some more. And Lisp is a family of languages, and we might say, hey, let's go and take this thing from Common Lisp 2, or let's go and take something from ML that's not in Lisp and add it too as a predefined function. So we'd like to make it extendable. And so what is the structure? What is the software architecture or design pattern that we use in the Lisp interpreter to make it easy to extend? You can make anything extendable. I can give you the source code and say, go edit it. That's a whole big deal about open source, right? You can take some code and edit it. And anybody done internship involving open source code? So what happens in your internships? Do you guys really modify that code? You use it, right? You add on to it. So what if it was not open source? What if it was just an API? What would you have lost? Other than the fact that you can't see the code. Not much from what from getting here. And there are times when I've gone and told people, hey, I'm using your code. Can you just change this one line to this line so that I can use it in a more flexible way? Please create a factory for me. And they say, oh, that'll take us some man years to do. Why don't you just do it yourself? And if I do it myself, any changes they make are lost to me now because I've got a separate repository. So I am an academic. What do I know about the real world, right? But I've never understood what is the big deal about open source. In fact, open source is a way to get lazy and not give you a proper API. So I do encourage you guys to look at Lisp Andrews interpreter so that you can implement your own operations. But I don't want you to go and change the files, like some of you have done, when you didn't know how to sort of reference the project. And so what exactly is the API provided to extend the Lisp interpreter to add new functions in Andrew? How do you do that? Again, if you've done it, you should know this easily. So maybe it's too easy a question, but let's assume that you're willing to answer an easy question. Too easy?
No, I don't know how. The way I did it is I looked at Andrew's source code, copy, paste, implements under it. So like I wouldn't have been able to do this assignment if I didn't know the functionality that previously existed. Therefore, I don't see the point in time.
So you're saying that to implement new operations, you use the source code from Andrew. I get that. I get that. And you can implement those operations on your own, but how did you tell Andrew's? Yeah. Okay. So we have a registry. And that registry is an API. And if you look at Andrew's code or don't look at Andrew's code, that's an orthogonal issue. Once you've implemented something, you can tell the registry, here's a new operation I have. Okay? So that is the software engineering framework concept to understand. That there's an operation manager object provided with an API. Okay? And you can say, here's a register evaluator. And each evaluator takes a string name saying, I want to add an operation with this name A or B and call this evaluator object of mine whenever somebody invokes this particular operation. Okay? So now I am not hostage to what is already defined. And once you've done the register evaluation, somehow the operation manager has to go and invoke your operation. So when the user types an operation, the operation manager goes and says, give me the evaluator. Okay? And it goes and asks the evaluator to evaluate itself. Okay? So I've given you an API to extend it. I've even given you the source code so that you can have a model for extending, but that is an orthogonal issue. Okay? And so I've got this operation manager, and that's a singleton because we have only one operation manager. So operation manager is the interface. Since it's a singleton, it's an object with an interface, we are going to create a class for it also. So we have a class name for it, and let's say that's basic operation manager. And then to get the particular operation manager from a factory, we can imagine that there's a word singleton after that class. And what does the evaluator do? The evaluator is given an S expression that was passed by the Lisp interpreter, is given the environment saying, there's the environment, go evaluate yourself. Go evaluate this S expression. Okay? So your plus evaluator will be given an S expression that starts with plus, a list that starts with plus. Your minus evaluator will be given an expression that starts with minus. And they are supposed to then know what to do. Okay? So far, so good? So who will call who will call get evaluator? Somewhere somebody has to call get evaluator, right? And and invoke the eval method on it. What object is going to call the get evaluator? The S expression object itself. So the user typed an S expression. Andrew's system created an input expression out of that. And that input S expression object is going to call eval, is going to call, is going to extract, is going to try to figure out what the function name is, function identifier is, use that function identifier to get the evaluator and say, hey, you do it. Okay? So this is all tying up now together, that as far as Lisp is concerned, every S expression evaluates itself, and we've added this layer ourselves, which is not something that we have to do as part of standard Lisp, so that we can have an extendable structure that we can offer to the students and extend gradually between assignments, so that you can extend the interpret. Okay? So somebody has to call the register evaluator too, and that can be done in your main method with a piece of code, or you can put that piece of code in a particular method, and you can put that method in a particular class and tell the world what the class is, and that's what we ask you to do. So we say go and implement a class that implements an operation registrar, which has got the register operations method in it, and that register operation method is going to call registrations on this particular manager segment. Okay, so that is just to structure your code. You can just put it all in the main, as some of you did initially, and we didn't require the registrar initially, but then people weren't registering, so we said let's make it explicit, and so this is something that we will look in assignment 2, that you've got an operation registrar or not. But in assignment 1, we just said, hey, because we didn't do it initially, just register the operations. Okay. So what you do is you call your main. In that main, you go and find the singleton, go and register your operations with the singleton, then go and call Andrew's main, which goes and registers its operations with the singleton, and then it goes and runs that read a value loop. Okay. So this is what we are doing now for your S expression. So for a composite S expression, not an atom S expression, a composite S expression, we go and use the basic operation manager singleton, we get it, we go and figure out what the identifier, we assume here that F is an identifier atom. Later we will assume that F is a lambda expression also, but for now we assume it's an identifier atom, and that identifier atom is one of the basic operations. And we go and get the evaluator and pass the buck to the evaluator. Okay? And we do the right get heads and get tails to do it. Okay? Questions? So I have now taken the Lisp interpreter and broken up into pieces. Okay? And I've got an operation manager and the remaining Lisp interpreter, which has got the parser, scanner, and so forth. And on top of the operation manager layer is the registrars that go and register operations with the operation manager. And I guess these two layers are not really, they can be they can be the same level too. And then you have the executors also, which are the ones that are registered. Okay. Actually, I got the layers wrong. The executors should be below that because the registrars know about the executors. So the executors are on top of the operation manager, and the registrars are on top of the executors because the registrars refer to the executors. Okay. Questions? And is this really what happens? I didn't implement the interpreter, so this is my, whatever I say is something I understand from Andrew's code. But there's a way to trace everything that's going on. Okay, so a Lisp interpreter is supposed to just give you the input, take the input and give you the output. But you can even trace what the interpreter is doing by doing some magic. And in this case, you just set tracing. And so if you want to do this yourself, in your main, just call main.lisp-interpret-trace-utility.set tracing, and you'll see the underlying operations. And you see that before any interaction occurs, a lot of these evaluators are registered. Okay. So let's look at one of these evaluators. Okay. like Nathan said, you actually he went in and we encourage you to do this in the document. You looked at Andrew's evaluators, you made a copy, and you figured out what to change. So you know what to change, but you should also know what was not changed. And Andrew wanted to write something more abstract, but he didn't get a chance. So this is my attempt at writing something more abstract, which would allow you to go and write your evaluators without having to look at his evaluator. Okay. So what have we got? We've got a structure of the form that I've shown here, where we've got the head node of this composite expression be a plus, okay? And the tail node point to a list that consists of two elements, E1 and E2, okay? This is assuming everything is correct, okay? So our input S expression is F E1 E2. And we have to evaluate S. We are calling an evaluator. So some S expression got created for plus F E1 and E2, and that went and called evaluate S environment. And now we've got, I'm trying to do two different pluses in this one plus. It could be an integer plus, it could be a double plus. Let's assume those are the only two kinds of pluses. So I have to go and figure out so I have to figure out whether my first expression E1 is a integer or a double, right? So I go and get the head and figure out which case it is, and get the values, add them up. Okay, and give a new instance of these values. Okay, makes sense? So again, this actually, I should have done it in more increments. So basically what I'm doing is I'm saying E1.getValue and E2.getValue plus E2.getValue, add them up. So nothing I present the first time is correct. If I pass plus 4, 5, I'll get a new integer of 9. If I do plus 4.3, 5.4, I'll get the addition of that, which is what, 9.7. And anybody can figure out, pass this enough to figure out what's wrong with it? Yeah. The tail could be you mean E1 or E2 could be composite? No, the tail is composite, right? We've got E1 and E2 as part of a list, right? And we are saying head points to E1 and tail points to E2 and nil. So which can be composite? Anything. Even could be composite. So what should I do? So this won't work, right? This will, if I go and enter plus 4, 5, 2, what will happen? So you need to call eval. Okay? That's a key thing. You do expect what you're adding to be integer atoms. You do expect that to happen. But what the user specified might not be an integer atom directly. The user might have specified a function application that results in an integer atom. Okay, so I was good here. I did an integer factory.new instance. I didn't just go and say get value plus get value 1 plus get value 2. But I did not call eval. So I'll call eval. Okay, so this is wrong. The get value is wrong. Okay. Actually, there's more than one value that's wrong. So I should really do, so I can convert that into an eval here. Replace get value with eval. No, why not? So let's assume we're not mixing doubles and integers. Should be fine. What plus are we talking about here? The plus that is used here, is it a Lisp plus or a Java plus? Can Java deal with the, and what is eval going to return? Which is is an S expression. So can the Java plus add up an S expression? So what should I do now? Yeah? Were you going to say something? No. Get its value. So we needed both eval and get value. So, and the new instance needs also, so that's, so we have to do, okay, I changed it at one place, I didn't change it at the other place, but I've got a get value directly, which I need to change also. I'll change for the next time. So I have to basically do eval environment dot get value for each argument. Okay. So getting this right, you know, this when to call eval, when to call the atomic things is not the most direct thing, and there are a lot of subtleties here. So this is sort of showing you how you essentially, you know, when you go in write a compiler, you have to go in reduce the distance between the native language and the machine language or assembly language and your language. Here I'm going to reduce the distance between Java and Lisp. Okay, so I'll correct this and we'll carry on from here next time. So to remind you, our Lisp interpreter takes input, produces output. That's the basic functionality. That's a very simple way to describe what it does. A more precise description is, and this happens in our Lisp interpreter. I'm not sure it really happens in C Lisp exactly this way, based on some test cases that students posted. We convert the input into an S expression first. That was done by Andrew's skeleton. And then to produce the output, we create another output S expression, which may or may not be the same as the input S expression. And we go and then call the toString method in that to go and give you the result. Okay? So the input is an S expression, the output is an S expression, and the user enters the input representation of the input S expression, and the user gets back the output representation of the output expression. Okay? So that's what we're doing. And we said that an input S expression, input and output textual representations are same, except that in the output S expressions you can have more kinds of S expressions than the input S expressions. Okay, so we said input S expressions will not contain tuples. I saw some post on Piazza saying that, look, you know, I saw in C Lisp this something dot something a dot b in the input, and I don't think Andrew's interpreter handles that, and I really don't understand, you know, how they modified the regular Lisp to support that. Okay, at this point. So that's important, and we've seen the output representations. You guys have implemented toString, so you know that quite well by now. And you know, atoms are just displayed by displaying their get value. Using Java to do so. Lists have parentheses rather than like curly braces in arrays in Java. And tuples have dots in between the head and tail. Okay? So looking at the output representation, you don't quite see this one common unifying concept of S expression there. We see three kinds of S expression: lists, tuples, and atoms. Okay? lists and tuples have these parentheses around there, so this seems that you could unite them. The atoms don't have any parentheses, so one of the questions in Piazza was, why are atoms called S expressions? Okay, and I like these kind of questions. It's good to go and ask the why questions rather than the what questions. What does the language do? It's more interesting to say, why does it do the way it does it? And often the answer has to do with implementation. So, I teach 401, I'm teaching this course, I teach distributed programming. In all of these language courses, you have to use programming languages. And people ask me details about programming languages. Does Java do this? Does Lisp do this? I don't have time to read up all the specifications. So what do? I say, okay, how would I design it? And how do I answer that question? By saying, how would I implement it? Okay, having taken compilers and written interpreters, I kind of have a feeling. So often the answers have to do with the implementation. Okay, we've seen. So here, what I did was I showed you two. I showed you things that you hadn't seen implemented yourself, like the define setQ, which we'll do in assignment 2. So this gives you an idea of how you actually represent. So the question is, why do we call atom and composite expressions as S expressions, and why are lists and composites united? Okay, and the answer has to do somewhat with the implementation. So you see the implementation here, that you see for atoms you have one slot, for lists and composites you have 2 slots. Okay, and you have some internal methods you can call on them. You can call get head and get tail on composites. You can call get value on atoms. So there we are seeing differences. The fact that you can call both get head and get tail on composites seems to indicate that they should be combined together. That's why the question didn't say why are lists and tuples the same. And you can call eval on both of these also. And you don't call, you have to also construct these objects. So we assume factories to go and construct these objects. Okay, so this is all internal. We can construct an atom, we can construct a composite. Okay. So now let's go and answer the question, why do we go and unite atoms and non-atoms? And one answer on Piazza, which I saw, was that, look, we need primitives, we need some building blocks, so atoms are the building blocks. Okay, and that's a good answer. But we see in Java that the building blocks are things like ints and strings that are called atoms here, and ints and doubles types are not objects. Okay, so they're not united together. We say, hey, objects are for things that collect primitive values together and not for the primitives themselves. So one can make a decision to not go and make the leaf level objects be the same thing as the parent objects. So why did we call both of them as expressions? What do we gain by doing so? So why do we call atom and non-atom S expressions? Atom and non-atoms, both S expressions in Lisp. Because they can be used.
They can be used just as they are. Like when I do a function and it gives me an S expression, I can do another function to that same S expression. It can be used as an input.
So you're saying the result of you're saying that an atom can be passed as an argument to a function that is a S expression, composite S expression, a list S expression, right? So you're saying that, but then I can do that in Java, right? I can go and pass primitives as arguments to methods on objects. So my basic question is that why this unifying thing? What are we gaining by this, Andrew?
Is it like some sort of like polymorphism type thing, where you're trying to, where you can like identify like, where they both like fit into the same sort of like blocks, like building blocks.
Okay.
But then you can like further identify like an atom from a composite.
So you're saying, okay, so this is the 2 things you're saying, and one is consistent with what Nathan said, that not only can you pass arguments to functions, but atoms to functions, but functions can return atoms. okay, which is what the second part of your answer is. But you're also saying that somehow you get polymorphism. And the word polymorphism is kind of used in multiple ways. So polymorphism and overloading are different. So no, but that's fine. You're in the right track. So overloading is that we have two operations with the same name, same signature, implemented. Overloading is operations with the same name but different signatures, and polymorphism is operations with the same signature and the same implementation. Okay, so you're talking of something in between right now, right? And what is the common operation you're thinking of right now, and what you see right here on your slide? They're both S expressions, and S expressions have what in common? All expressions must have an eval. Sure, they differ in some ways, but they both have an eval. And the nice thing there, and what's nice about having a common eval in both composites and leaves? And you guys have written a lot of evaluators, you made use of this feature. So we're building a tree, and often we have to evaluate a node somewhere in the tree. Is that eval recursive? Yes. So it's recursive because it calls eval on itself, or it calls eval on its children. So I don't know whether this is recursive or not. It is calling eval, that may be a different eval. So recursion normally means same implementation. But that is the key here. That if the eval on a node calls eval on its children, that eval can be oblivious to the fact whether the child is an atom or a non-atom. It can just say eval, and the atom will evaluate itself in one way, and non-atom will evaluate itself another way. Okay? So this is actually a design pattern. So why unite atomic and thing? So we have this eval in both. And recursive eval is, and I'll use the word recursive within quotes because it may go and call a different eval. Okay, so that's a different signature, same signature but different. It's called subtype polymorphism. And there's something called a composite design pattern. The composite design pattern says that we have a composite object that has children, and the composite and the children both share a common interface. The composite can implement more methods than the child may, but the fact that they share some interface in common makes a design pattern composite. Okay? And what we are really doing here is using the composite design pattern in Lisp, and we are calling both atoms and non-atoms as S expressions because they both evaluate themselves. Okay? So that's a long answer to the short question that was asked. And again, I encourage you guys to ask these questions because those are the questions that are of interest here. The details of C-Lisp and whether load takes an extra argument or not are really things that are not that interesting but useful.
I remember you have a similar statements when you talk about small talk. All the data type are united in one data type. You said that relates to the nature of
Nature of?
Interpretation language or?
No, Smalltalk was compiled. It had an interactive component too that you could type in the expressions. Just because you're interpreted doesn't mean that you're not compiled. You can be compiled. It doesn't have to do with interpreted versus compiled. It has to do with just having a common abstraction. Okay? As it turns out, to make that efficient, they had to restrict, they had to use one bit in each integer to indicate whether it's a pointer or it's actually a value. So in each word, there was one bit used to indicate whether it's a primitive object or it's a pointer to a composite object. So you lost one bit. Okay? There were some trade-offs, and in Java, objects happen to have these wait and notify queues, and to go and put these queues in each int is way too wasteful. So one can imagine not doing unification for that reason, but because everything is an object in Smalltalk, I can call toString on anything. Whereas in Java, if I want to go and change, if I want to print, get the string representative of an int, I have to go and call a method called integer.convert to string, whatever the method is, and pass the primitive value. Or what I do lazily is I just go and add to a empty string the int, and I get back the string representation. So you have to be a little bit more awkward in Java than in Smalltalk, because you can't invoke the toString operation on each object. On an int, you can't do await and notify. Okay, so you lose something, and you have to do cases. So I'm just talking the pros and cons. Anything in systems has pros and cons. Okay, so that's another point I want to make, especially because we are in a class that says programming languages. Okay, plural form means that more than one language is worth discussing, which means there must be pros and cons because they must be doing the same thing in different ways. Okay. Other questions? Okay. So this is so. Like I said, you create these composites and you use the factories to do so. And here you're seeing what you input to create these expressions. Okay. So you go and just input the output value for an atom, and the atom is created. Okay. And for a composite, you don't say 5.6. Okay, you call functions to do the creation, and the function that you've been seeing is cons. Okay, so we see here now both the input representation of S expressions and also the internal representation. Okay, and you don't call getHead directly. If you've already given an S expression, you can create another composite S expression or an atom S expression by doing a car. Okay, so we've seen that also. Okay, and you can get another S expression by doing a cutter. Okay, so with cons, car, and cutter, you can, and with entering atoms, you can go and create all kinds of S expressions. And here I'm talking about the input rather than the output. Okay, it's the output of the input S expression which creates the output S expression. Okay, and there I'm sort of showing you the elephant by showing you parts of it, and you don't quite see the whole elephant. But we did see the elephant earlier on, which probably you've forgotten by now. But we saw when in our review or tour of different languages how these things could be used to do something meaningful. And the meaningful thing there was figuring out whether somebody passes or not. And we saw setQ, which you haven't implemented, but which you will have to implement in assignment 2, which is an assignment. And we saw defun, which was a function definition. And I explained these things by analogy with other languages, okay, rather than describing them precisely. I said, setQ is assign and defun is function definition. And you can give a name, parameters, and then the body is another S expression. And we use a prefix notation. Okay, so this gives you an idea of how it all works out. That what you see on the left is the input expressions you input. On the right, you see the output, the toString representation of the S expressions that are actually created from the input S expression. Okay, so you're seeing we didn't talk of S expressions at that time, but that's what's happening underneath. Okay, and we saw some more fancy stuff too. We saw that we can actually have lambdas, which are these blocks, and you can assign a lambda to a variable. And a lambda takes parameters, just like a block, except it doesn't have a name. And that block can be then assigned to a variable. Okay? And so we kind of got an idea of how this works. I won't belabor this again because we did talk about it earlier. And when we talk about the implementation, we'll go and look at this in real depth. Okay? And also in your assignment 1, you have been writing some list, not anything meaningful, to test your constructs, but you're getting a feeling for what's happening underneath through that. And again, you see on the input, there are no dots there. If I go and put a 4.5, if I put in a C Lisp, this thing, it'll fail. If I put it in our interpreter, it will fail. Okay, so this is not allowed. You want a composite, you go and say cons 4.5. Okay, you can't just say 4.5. Okay, so it's all function application at the input. Now that might, okay, I'll talk about that a little bit. And I didn't really show you anything interesting about Lisp. I showed you how Lisp can behave like Java, but I didn't quite show you what it's really used for, which is recursion. So look at this code here. You know more or less what you need to know to interpret it in your head. And it is a recursive method. So look at this code on the left and try to figure out what it does, okay? And answer the following questions. If this is recursive, what are the base cases? Is there one base case or more than one base case? And if there is recursion, where is the recursion? And whenever you do recursive method, you don't just call yourself directly. If you call yourself directly, you will run into a Stack Overflow problem. By the way, I did see one message, maybe it was a private or a public message, I didn't get a chance, but I saw it in my mail, where somebody was saying, look, I'm getting this error from local checks, and I saw a Stack Overflow error there. Okay, so you guys are writing recursive methods, so I'm not surprised you're getting a Stack Overflow method there, problem there. So you want to not overflow the stack, which means you must reduce the problem somehow. Okay, so again, this is defun. You haven't quite implemented it, but defun is just saying function definition. F is the function name. L and E are its arguments. Okay, parameters. Everything after that is things that you've implemented. So we are doing a conditional, and we've got 3 cases. So what are the base cases here? Some of you probably figured out what the function does. Keep that to yourself right now. Just tell me what the base case or cases are. Okay, tell me what the recursive steps are. Whatever is not recursive is a base case.
It's going through the list. What the recursive step is. It's basically like traveling through the list and then moving one over each time.
So the call of F, Cutter L, E is the recursive step, right? Okay, so that's the recursive step, and you're telling me kind of what it's doing. So I'm given a list. I'm given an argument, and so that is a recursive step. That means the first 2 cases must be the base cases. So what's the first base case checking? That given an argument L, it checks whether it is nil. Okay, which if it's given a list would mean that the list is empty, right? So the list is empty, I give the answer nil. The second base case is, say it in English. Is E equal? Is E equal to the head of the list? So I take the first item in the list and see whether E is equal to that. Okay, so E must mean an element type. L must mean the list type. And if it is equal, I say true. Otherwise, what am I doing in English? Explain the recursive step. Sorry, both of you were within the same line. Okay, I'll let Ben answer.
Recall it with the rest of the list.
So checking if the rest of the list, is that what you were going to say too? So it checks whether E, it's just calling with the rest of the list. So ultimately, if I was to give F a good name, what would be a good name for F? Find. Sorry? Contains. One more name? Okay. So good. You know, by the way, people hate thinking of names. I've seen people program and they want to just give the variables X, Y, and Z, and I'm saying, name it. I said, no, that's a headache. We've got to think about what it really does. So this is, I would have called it member. Is E a member of L or not? Okay? Depending on which you're looking at. Whether you're looking at L, then it contains. If you're looking at E, you're saying, am I a member? Okay? So this kind of reduction is actually called tail recursion. You can see why? That I'm given an argument, and my recursive step takes I'm given a list or a composite object, and my recursive step applies me the function, to the tail of the composite object. Okay? So tail recursion is a term that was invented in the context of Lisp, but whenever you go and apply a function to the rest of the list, in any language, the literate term is tail recursion for that. Okay? That's otherwise, actually there's no other term for that I can think of. Okay? So it's called tail recursion. There's number recursion, there's different kinds of recursions, and this is tail recursion. Okay? That doesn't mean in Lisp you can't have both head and tail recursion, that you can't call the function both on your card and your cutter. Okay? In fact, you'll have to do that in assignment 2, part 1, task that I published. So you can do both. You can do a full tree recursion, but this is more a Lisp recursion. This is the kind of recursion you typically see in Lisp. Okay? So you're now seeing Lisp as it was typically used. And what is the function list? Return E member of L. Questions? So we are understanding our read eval print loop. And we've seen what kind of input we have to give to create S expressions. And atom is created by entering its output representation directly. Atoms are created that way. Composites are created by invoking a function to create them. Okay, and this, from the messages I've seen on Piazza, is causing a lot of confusion, and maybe it causes me confusion too, that I've somehow wrestled with. And why is that confusing? Because, in Java, a list is like an array. I don't call a function to create an array. I just go and list the elements. And that's why one Piazza question a long time ago said, why can't I just go and enter left paren 5.6, right paren, and that's my composite. So that's not the Lisp philosophy. And, it's just making things explicit that are implicit in other languages. When you go and enter 5, 6, somebody internally is executing some code to take your 5 and 6 and create an array out of it. So there is some function being called there. And actually, those of you who know Java well, is there another way to create a list, an array that actually involves invoking an operation? To create an array constant, I'm saying, not an array variable. Array variables is fine. But is there an operation to create an array that you have to give? Yeah.
Is there something in the array class to do that?
So is there something in the array class to do that? You're saying there is, or you're asking me?
I think there is.
So array, so that's an interesting thing. Think of classes and objects. Creating an array is creating an object, right? And I just enter the elements of the object. Forget arrays now. Let's say point is a class that exists, which does the java.awt.point. What do I do to create a point containing the values 5 and 6? Supposing the class is called point. Sorry? New point with 5, 6. New is an operation. It's not quite an operation in class point. It's something outside. Okay, so the operation to create an object cannot be in the object. Otherwise you get into a bootstrapping problem. But it is an operation somewhere. Okay? And in an array, can you create an array using new also? Has anybody done that? So is this idea in other languages that functions thing? I can say something like this. Okay, I can say I want a new int and then go and give those arguments. And if you're inside a piece of code, if you're passing a parameter to a function, you have to do something like this. And that parameter happens to be a constant array. You have to do something like this. You can't just put within curly braces 5, 6. Okay? So in some sense, when you're in execution loop, even in Java, you have to go and do something like this. And a new point 5, 6. So that's an analogy here to sort of, for those of you who are confused about why we have to have this operation name. Okay? And remember, the word new is not stored anywhere with point. It's not stored anywhere with array. That's another thing that was causing a lot of people confusion with quotes and evals that I saw. New is just the operation you used to create the array. Okay? it goes away afterwards. Okay, just as when you do a compiler, a lot of things go away by the time things execute. Okay, if the variable names go away, they get replaced by offsets. So in an interpreter, the operation you use to create the object is not stored with the object, it goes away. Now you have the object. Okay? So when we look at quote and eval, that will become more clear. But that's an important idea. Questions? Okay, so a little bit more understanding of this picture. Okay, we're going to spend a lot of time understanding. So that brings us to sort of, we understand input expressions, we understand output expressions. So then the challenge and the reason why we need to spend a lot of time on that picture is that we have to figure out this eval. Okay, we haven't handled enough input representations to do the full eval. Okay, and we're going to break that up into parts. And in fact, these 3 parts we're going to further break down into subparts based on the assignment. So your assignment 2 that you're going to get is not going to be the assignment 2 I visualized when I first thought of this, okay, which was very abstract at that time. Okay, but we know what assignment 1 was, which was basic functions in Lisp. And you guys have taken Andrew's code and you've extended it, and it's amazing how much you can do by analogy. It's also a lot of things you don't understand when you do things by analogy. And so the point of the remaining lecture today and maybe some next time is to sort of help you understand what you actually did. Okay? And to help you understand what you actually did, you need to also understand what Andrew did. And you're responsible for knowing both things. Okay? To some degree, to the degree I'm going to talk about. So we said, okay, we have to do this eval. The eval can be on atoms, and it can be, so we know that we can't contain any tuples. So our input as expression must be either an atom or a list with sublists and atoms in it. Okay, so that's a general form, and we are going to it's going to take us a while to get to this general form. Okay, so we went and said let's simplify things. We'll make A to be a non-identifier atom, a literal. Okay, so let's go and deal with that case first. So no variables. Okay, variables come later. And we'll make our list of sublists be a list in which the first element is an atom, okay, and it's an identifier atom. And so if an identifier appears, it has to appear within a list. It can't just appear on its own at the top level. And the remaining elements of that list are going to be arguments that we give to the function. Okay, so that's what our input expression is going to be. And not only that, this function is going to be a function that identifies a basic function. What's a basic function? 2 characteristics. First, it's implemented in Java. Everything is it's not something that everything that we want to get directly from Java, we'll implement in Java. I mean, that is not implemented as Lisp, we'll implement in Java. And also the function mirrors what the Lisp function should do. Okay, so we have plus in Java adds things up, plus in basic function also will add things up. We will have Java implementations of functions that are peculiar to Lisp only. Okay, that's not, so we looked at that, and I'll go and classify them again into these 2 categories later, I believe. So we then first said, let's go and figure out the simplest case, that A, where A is a non-variable atom. Okay, it's a literal atom. So we actually came up with 2 answers, and then after the class, Ruben came to me and said, hey, what about the third answer, which is much better, and which was indeed much better, and which was indeed what was implemented by Andrew. So let's come up with the worst answer. Okay, the worst answer is we are going to say, okay, we have a get value in the expression, so we are going to just return in eval a.get value. And why was this not acceptable? Anybody remember? Excellent. So what's your name? What? Sam? So we can't return this. Okay, we have to return an S expression. So we can't quite return that. So this was my second answer, which we left at. And we said that, look, now we are going to have an eval in each kind of atom, integer atom, double atom, string atom. And it's going to go and create a new instance, new S expression, and give get value as an argument to that factory, the constructor. Okay? So this will work. Okay, any dispute with this? Now, I didn't like this. Ruben didn't like this answer, and this was not the answer I wanted to end with. So what's wrong with this answer? It works, and yet it's wrong, right? People often tell me, why am I losing points here? It works. And I always say, there's style points. Okay, it has to work in a certain way. So what style points are we losing by doing this? One problem is that for each atom I've got to go, and each kind of atom I've got to go and have a separate eval. That's one problem. So here's the hint. So that's one problem. And here's a feature that we are not using. We know A is immutable. So given this fact, which we've forgotten, all expressions are immutable, how can we make this more efficient? So just use a singleton. So each time, so that's a very good point. That every time I want to return 10, I can go and look up a table and say, what atom have I got stored for 10, and just return that atom again and again. But then that requires a lookup. I don't want to do a lookup either. Only Ruben knows the answer. Just return the atom itself. Okay, we just instinctively said that if we are doing an eval on an atom, we should be invoking get value. No, just return the atom itself, and that will give you the S expression that represents the atom. Okay. So we are going to go and just return A. Okay. And that might seem unintuitive, but when we go and look at pluses and minuses and so forth, they will go and look at the atom and call get value at that point. Okay, right now our job is that eval returns an S expression. Okay, so we can't go and return something else. So when we implement the basic operations like plus, at that point the get value is accessed. So in the function we will do that, but when we just have to go and eval an atom, we just return the atom itself. Okay? Questions? Okay, so we're done with atoms. That was the easy case. Now we have to go and deal with all these different kinds of functions. Okay, different things have to happen for different functions, and this is what I was trying to say earlier when I drew a picture. That now we're going to talk of these functions as being in two classes. One are the Lisp specific operations, and these are atom, con, scar, cutter, and so forth. And the others are the regular operations that refer to other language. We'll call them both basic operations. Okay. And to make our life more interesting and to make this assignment one doable, we said that we will go with an extendable system. And an extendable system doesn't mean that you take our code and modify it, our procedures and functions. You treat our code as a black box, ideally to add more functionality, and you go and add to that black box. Okay, so we went and said we're going to have one eval for all composite expressions. Just a single eval. And that eval is going to figure out what to do for each function. Okay, that seems like a bad idea because this one eval has to do a little switch statement perhaps and go and say if operation is this, do this, if operation is this, do this. And switches are always bad. Okay, not always bad, otherwise switches won't exist. But switches are often wrong, often bad. Okay, so object-oriented programming sometimes gets rid of a lot of switches, okay, because the right method is chosen automatically by Java. And another way to get rid of switches is using a table, okay, which you can use in any language. So we said, look, we'll use a table, and this eval will just read the table. It doesn't have to go and worry about how the table was populated. Okay, that's a common technique used in writing modular code. Okay, so so what's the table? That table, who maintains that table? Not S expression. Okay, that's doing too many things. There's a principle that those of you who have taken previous classes from me know, which is separation of concerns. That we don't go and do whatever things can be separated, we do in separate classes. So this seems to be orthogonal to S expression evaluation, or it can be done independently. So we'll have a basic operation manager. We'll have a global table, okay, singleton, and there'll be an object that keeps that table, and that object will take the function name, get a string representation. Okay, it knows it's an atom. Now, because it's an atom, it'll go and invoke some atom-specific operation, and get the string representation, use that as an index into a table, and find an evaluator for that function, and pass to the evaluator the S expression that was to be evaluated. Okay, so so that's what we're going to do. Okay, so an S expression goes and figures out what evaluator to use and passes itself to that, and also passes an environment to it. Okay, and we saw last time that environment is something that we will use to keep track of. When we implement functions, we need to go and keep track of the scope and what variables are assigned what values. So the environment will go and keep track of what values are assigned to variables, and that is something we will need eventually, not right now, because we are not dealing with assignment of variables. Okay? Questions so far? So this is important. A lot of you guys weren't getting what the operation manager was doing. Okay? And so it's a composite expression, and it's delegating the job to somebody else. It is not an instance, and it's not a subtype of the table. It is using the table. And so this is our operation manager. The operation manager has a register method that says, hey, given this name, here's an evaluator. And then it has a get evaluator method that goes and says, given this name, give me the evaluator. Okay. And again, so the question is, who invokes the operation manager function methods? And you can always go and say, okay, the main method, before it starts, it goes and invokes it on the operation manager, all the things it wants to do. Okay, that's making main a little too bulky. The task of registering is a separate task that you can define. So we said that, look, that should be in a register operations method that is defined in an operation registrar. Okay, it should be an operation register method first. That's one decision. Second, it should be in a separate class. Why not? That's something that can be written independently of anything else. And not only that, that class should implement an interface. Why that? Well, we can try to work with different versions of Lisp. So when we are testing your code, we can first go and register all the operations that Andrew built, test the code. Then we can incrementally add your operations and test the code there. We don't know what your, to do that, we need to find your registrar. So that is why you have to register your operation registrar, ideally, with the class registry, that's the grader, so that we can go and find your method, so that we can call your method and we can deal with multiple versions of Lisp, and that's just gives you more flexibility. Okay, so that's something we did not check in assignment 1, but we recommended you do it, and in assignment 2 you will have to do it. Okay, so we will have a check for that. Questions on this? Okay, so this is the full picture that, like I said, you guys, changed things around, got things working, but you're responsible for knowing the whole picture. Okay. So I have a typo here, but you can have multiple registrars to experiment with different sets of operations. And tests can register custom operations without calling the read eval print loop in main. So what am I doing right now? The template I gave to Zishan was that I call your main and I immediately end it. So I call your main with dot. That allows you to register the operations, and all the input I go and give through the input line method of the Lisp interpreter. Okay. But with this, I could have just gone and not even had to call your main. Okay, so I got the animation in the opposite order. So this is the question answered by this. Okay, so all of this stuff we did earlier, but it's good to sort of get this all covered again. So this is also something we did last time. But let's look at it in depth. So let's go and see how Andrew implemented the plus evaluator. Okay, a lot of you have taken plus or some other evaluator he implemented and modified it to get your stuff working. Okay, so it's important to know what he did. So what's the form here? We're given an S expression, which is a function call. That function call is to plus, and it takes two arguments, E1 and E2. So we'll assume there's no errors at all. Okay. And the structure of the S expression is on my left. I hope I haven't made a mistake there. But the head of the list is, of course, plus. And then we take the remaining part of the, and so we can actually extract these parts out. I can get E1 out, and then I can get E2 out. And whenever you'll be extracting elements from a list, the last operation must be a head. Okay? And then, because head is the content, and tail is the next link pointer. So you're either going and getting it from the current link, or you're getting it from the next link, or the next to next link, and so forth, but you're getting the head operation. Okay? So I could go and say, I have to return a value, so let's go and put a template return. And I could say E1, I have to add these two ups, so I can say E1 plus E2. Okay, and if I say that, how am I wrong? I've got some blank spaces there, so I must be wrong in some way. So you don't know what type of atom they are. So that's good. What I did was, to make my life easy, last time I just created a very confusing slide because I was talking of int and double. Let's assume this is plus int. Let's assume we can, without loss of generality, as they say, let's go and reduce the problem details. You have to evaluate E1 and E2. Andrew suggested they were atoms. You're saying, sorry? Hang on, Andrew suggested that. I was not saying I was agreeing with that. Don't back off, guys. Okay? So Andrew suggested that, and I'm suggesting you don't accept his suggestion. They don't have to be, right? These are arbitrary expressions. So you should be evaluating them rather than just using them directly. Okay, so I evaluate them and I get another S expression back. Am I still fine? What is this plus I'm talking about? This is Java plus. I mean, I can't recursively call plus and plus, right? So this is that is the plus from Lisp, and this is the Java plus. Sorry? You just can't add X expressions. Okay, so the fact that our atom eval returned an expression rather than the value is causing us headaches now. And what did I say? So what should we do then? Get value. Now, the results of X expressions are atoms, and they are int atoms. So he was right. He was just thinking ahead and was assuming an eval. So you both guys together have got it, that you need the eval and then we have the atoms. Okay? So we need a get value somewhere. If E1 and E2 were directly atoms, I could have called get value direct. But in fact, oh, and also I have to have I have to do the backward conversion too. I've got to return an S expression. We know we're talking of integers. So I can't just go and return the value back. I'll get a type error. So I have to go and create an atom out of it, a new atom. Okay. So if I enter +4, 5, that'll be fine. I'll create this int atom. But if I do +4, 5, 2, that's where Ben's what I've got on my slide will not work, and I have to go and do an eval environment. Okay? And that will work. Okay, and now you see that eval is calling eval. Okay, the kind of top-down eval that we were talking about is happening. Okay? I had to spend a lot of time making these slides, okay, to have this kind of animation. Questions? You appreciate that? Thank you. Okay, and can we convince ourselves this is really happening? So I didn't write the Lisp interpreter, and I'm always a little insecure about having done things right because I didn't implement, and we only learned through implementation. So, but I put traces in his interpreter to figure out what he's doing, and I wanted to make sure his trace statement is consistent with what I said. And in fact, you guys can do this too. Okay, when you get the new Lisp interpreter, by the way, the new Lisp interpreter will require you to make some changes to your previous code to make things work. And I suspect anybody who's in class right now, this question will be irrelevant to. But is there anybody who hasn't loaded the Lisp interpreter so far on your computer who is willing to admit it? So even if, please make sure that you, and I'll put a Piazza message too, please make sure that you load the current Lisp interpreter to get assignment 1 working, because we do have grace days in assignment 1. Grace days meaning you have late points. Because when we go and release the new Lisp interpreter, your assignment 1 will break in a very organized way, but it'll take some time. So anyway, the new Lisp interpreter will have this tracing ability for you also. So let's go and see what's happening. You enter, or I entered +452. A lot of tracing will go and tell you what Andrew's interpreter does to create an input S expression out of it. Okay, that is not magic. That's a very hard part. That has a passing involved. So at the end of that, we have an S expression, a composite S expression, which has the display plus, comma, +452. So that's the input S expression. And what you see on the left of that display is the class that created that. And S expressions classes are defined by you. Okay, the basic S expression is defined by Andrew, but you have to subclass that. And the latest subclass we have from Andrew is called lambda calling S expression, because we're getting ready for assignment 2. Assignment 2, the S expression will call lambdas. So we have this S expression whose representation is plus is the operation, and then we have a list of the arguments. Okay, that's what we see. That's what we've got. And now we are going to see the steps taken by eval of this input S expression. Okay, so it's going to call evaluation on the full on each of its arguments. That eval will call eval on its sublist. So basically, the evals will be called from bottom up. I mean, they'll be called top down, but the return values bottom up. Okay, and we're only printing the return values. So the very first eval that returns a value is 4. Then the next, and it just returns 4 itself. We see that no new atom was created in this process. Whenever an atom is created, we print that out. No new atom was created. Then 5 returns. So it returns itself, the same atom. And we just go and print out the value in the atom representation. Then the plus is called on 4 and 5. That plus internally creates a new atom, integer atom, with the number 9. Okay, we know a new atom was created here because I've got this term integer atom number 9. And now that we have that 9, we can call the eval can, and so that was done in eval, and the eval goes and returns the value of that integer atom. So eval, as a side effect, created that integer atom and returns that value. Then 2 gets evaluated. We're evaluating left to right. And the top level eval then, as part of its function, goes and creates an integer atom with 11, and then returns that 11 as the value. Okay? So you're seeing essentially what I said earlier. You're seeing the steps there. Okay? So new atoms are created only for the atoms not in input S expression. Okay? And just to drive the point home, so you guys have been using Object Editor. Those of you who've done 401 with me actually used the Object Editor directly and created UIs of various kinds. And indirectly, you guys use Object Editor because I created the testing framework using Object Editor. And here I've used Object Editor to go and visualize the input and output S expression. So you see the input S expression is this complicated thing with nested lists. Okay, and the result S expression is just this atom 11. Okay, so this shows you the hierarchy that, I showed earlier is being visualized here. Okay, again, I'm just using tools to make sure I'm doing things correctly. And that's the value. Okay. Once you know how plus works, minus and or, they're going to be very similar. Okay. So nothing else has to be mentioned at that point here. Okay, so we've covered the whole category through plus. So the interesting thing now becomes, how are the Lisp functions implemented? They're all implemented differently, and more importantly, by looking at their implementation, I will understand how they behave, really understand how they behave. We understood how they behave by analogy with Java, okay, but we want to really understand now and answer the kind of questions that I see on Piazza. What does code do in this case? What does con do in this case? As I was walking down, I heard somebody say, I really don't understand what con does, okay, and that's good. The more you know what you don't know. So it's good.